Okay, so starting over again because it's now 11:35. So today I'm going to talk about sorting, in particular merge sort and quick sort and quick select, which you saw in the tutorials a little over a week ago. Okay. So merge sort, hands up if you know merge sorts. Good, good. Okay, so just to review, merge sort. For merge sort, we're given an array A of n elements, say. So I know you probably can't see the board, but the camera is better than my laptop's webcam. So we split it into two subarrays, say A1, which is going to be from 1 to ceiling of n over 2, and A2, which is 1 to floor of n over 2, and sort 1 and sort each recursively. So, let's say it's only interesting when n is greater or equal to 1, sorry, n greater than 1, each recursively. When we get down to arrays, an array of size 1, we stop. Okay? And then, after we've sorted A1 and A2, we merge them. So to merge them, we just take them. Somebody left. Oh, reconnecting. Okay, so we take them, so they're now sorted. We look at them, we look at the first element of each one, and whichever is smaller, we take that. And now, whatever was second in line is now at the front. So again, we look at whatever is smallest and we take that. So, you know, if we have say 7, 11, 19, 25, and then we have 8, 10, 17, 21, 23, then what are we going to do? We're going to look, 7 is smaller, we take 7. Okay, we look, 8 is smaller than 11, we take 11, sorry, we take 8, 10 is smaller than 11, we take 10, 11 is smaller than 17, okay, 17 is smaller than 19, 19 is smaller than 21, 21 is smaller than 25, sorry, is smaller than 25, so we take 21, 23 is smaller than 25, and so we get this sorted list. How much time does this take? Well, it takes linear time. So, what is the recurrence? T of n. So notice that for each comparison we do, we put one thing in the sorted list. So we're going to do n comparisons. So Tn, the splitting is easy. So it's 2 times t, and remember, when we're using the master theorem, we can ignore floors and ceilings, so it's n over 2 plus n. So the splitting we ignore. The merging costs us n. So we look at the master theorem. So remember, this is the case. So what is f of n? So a equals 2, b equals 2. Remember, you don't need to memorize the master theorem because I will always give it to you. And f of n equals n. So in this case, f of n equals theta n to the log base b of a, because log base b of a is 1. So n to the log base b of a is n, which is f of n. So, yeah. So we get that t of n equals theta n log n. So actually, this is n to the log base b of a, but that's just 1. So we get n log n. So that was easy. So merge sort, worst case running time is n log n. Any questions? No. Everyone, have you seen that? You've seen merge sort before. Have you seen the analysis before? Don't know. No. Good. Okay, so this is an easy case of the master theorem. Okay. So merge sort is nice because, well, it has all kinds of nice properties. It's going to come up again in a few days because I'm going to talk about the merging step and make it a bit more interesting. People use merge sort because it is pretty fast, but it's not usually as fast as quicksort. Okay? In practice, a lot of people use quicksort. So, why? So let's look at. Have people seen quicksort? Ooh, yes. Okay. Here are. Okay. So just so the thing is, quicksort has. I mean, there's the simple version, and then there are the more complicated versions. So the simple version, some people when they first teach it, they're like, oh well, what do you do with quicksort? You get an array. So given an array A of more than one element, well, we actually still split it into 2 subarrays, sort of. But differently. So in merge sort, we just split it into 2 subarrays. We cut it in half, roughly half. With quicksort, we choose a pivot. Okay. Now, some people, when they teach quicksort, they say you choose the first element as a pivot. In practice, people don't usually do that. Why? Well, let's see what happens if you choose. Okay, well no, this is not merge sort anymore, this is quicksort. That's way too far left. Okay, can you read the board at all? Me? No? Yeah, really? Wow. Yeah, okay. So I went and got the camera. The thing is, I spent last night actually fighting with a piece of software which turns my phone into a webcam. So my phone is connected to the Wi-Fi, the laptop is connected to the Wi-Fi, and you install this software called, I forget. But yeah, and so that's why I have bags under my eyes. I was up late fighting with the phone. The problem is, and it's like, yeah, it is. So it's nice. It's fairly decent resolution. It's better than the webcam, but and it worked. It worked. I could wander around. And the phone works as a webcam. I can walk around the apartment with it because it's connecting through the Wi-Fi. I was like, great, it's set up. I tried it with Zoom. I could record the stuff with Zoom, everything like that. I paid for the professional version, which is like an extra $5, so that I could mirror the image and I could like adjust it and zoom in and zoom out and everything. I was all happy until I tried it on Collaborate Ultra, and Collaborate Ultra will not talk to the phone, it will only talk to the webcam. So that was useless. I mean, I could run this session through Zoom, but I should be recording this, but I'm recording it on the little camera anyway, I hope. Yeah, it's still recording. Okay. Until it runs out of the memory card. So, what's the problem with choosing the first element as a pivot? Has anybody seen what goes wrong if you choose the first element as a pivot? Okay. Okay, so let's suppose that I accidentally call quicksort twice. Right, so I give it some array, I call it, and then I call it again, but the second time it's going to be on a sorted array. So let's see what happens if I give it, oh, I shouldn't have erased that. So I give it 1, 2, 3, up to n. Say, oh, actually, you wouldn't use, later in the second half of the lecture I'll explain why you wouldn't do this with quicksort. But, okay, suppose these are the ranks, not actually numbers. Then what are you going to do? You're going to take 1, and you're going to run through the array and separate it into stuff bigger than 1 and stuff smaller than 1. And the stuff smaller than 1 is, at most 1 is 1, and everything else is bigger than 1. So that's terrible, because your split didn't really do you any good. You spent linear time just to find the minimum. It's the same way if somebody gives you an array and it's sorted in reverse. Okay, so what some people do is they pick 3 and then they take the middle one of those 3. So it's median of 3. Now, all of this, so the idea is, don't pick like a particular place always. Choose some position uniformly at random. Okay? Because if you're lucky, it will roughly split the array in half. People have seen that before. Why not take the max value divided by 2? In this particular case, oh, well, if it's sorted, then you could just stop. If it's not sorted, first of all, you don't know what the max value is. I mean, you can run through in linear time and find the max value. And in a case like this, where they're consecutive, where the number is from 1 to n, then yes, that would work. But in general, you don't know anything about the numbers. So that also falls apart on when I give you something like 107, 263, 95, 41, blah, blah, blah. And then over here, you know, I have 302. Yeah, let's move this even further over. And then here I have 5 million, no, 501 million, yeah, 501,643,247, something like that. So I have all these little numbers, relatively little numbers. Yeah, so the idea is you have the array and you're just gonna pick like there. 41 is my pivot. It could stink. You could by accident pick the smallest number or the biggest number, in which case it will split the same way as before. It will be like, okay, so 41 happens to be the smallest number. It could be when I do this, what is smaller, what is less than or equal, 41, what is bigger, everything else. Okay? So it could be that if you're unlucky, what's going to happen is this is going to be, you pick the smallest. Now, oops, you accidentally picked the largest. Okay. So now this one you choose 501, 643, 247. Okay. And so over here, now you're going to pick, now you have the array. What's the, okay, so now say you have 43. So it could be that you're going to get, when you look at the execution, it's going to be a degenerate tree. Okay? So what's the problem? Well, if you look at each level, if you look at each of these nodes, you're performing linear work. Okay? So you're doing order n work because, you pick the pivot and then you go through and you split. And then you come down here and you do n minus 1 work. And then here you're going to do n minus 2 work. And then n minus 3 work. Now in general, the key thing about quicksort is when you you can still view it as a tree even if you split it in the middle. So for example, if we choose 263, okay, if we choose 263 as the pivot, then this is going to go into 107 and 263 and 95. Oh no, this is done. Let's say we choose 107, because otherwise it looks like this half is going over here. So we just choose 107, so it's 107 and 95 and 41 and so on and so on. And then over here we get 263 and 302 and 501, blah blah blah. Okay. So, what can you say about these numbers? Well, this is going to be sum n1, and this is going to be sum n2. And when I do a split here, how much work am I going to do? I'm going to do like n1 work. And when I do a split here, how much work am I going to do? I'm going to do n2 work. When you sum these up, it's still n. So down here, whatever this size is, n3, n4, n5, n6, the sum of n3 plus n4 plus n5 plus n6 is still n. So at every level of the tree, you're doing linear work. The problem is, if you choose the smallest, how deep is the tree? Well, if you choose the smallest or the biggest at each step, then the tree has depth n. So you end up doing how much work? Like n plus n minus 1 plus n minus 2 plus n minus 3, da 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 da, down to 4 plus 3 plus 2 plus 1. Okay? So you do n squared. Okay, so in the worst case, quicksort takes n squared time. In the Now, I remember I said I don't talk about the best case, but in the best case, quicksort takes n log n. Now, you can actually do that by analyzing quicksort, or, as we're going to do in the second half of the lecture, you can prove that a broad class of algorithms, which includes quicksort, can't beat n log n. And in fact, in general, you can't beat n log n sorting. Okay, so now let's talk about the analysis of quicksort. So, let's think of this tree. There is an analysis in the book which is very heavy on occurrences and bounding summations and stuff like that. And if you want to practice summations and everything, that's great. But it gives you work on your skills and you get better at that kind of stuff. But it doesn't teach you sort of a tool. It teaches you a skill set. But you can read it in the book. I want to teach it to a slightly different way, because this gives you a powerful tool. Well, it gives you an idea of how to use a powerful tool called Chernoff bounds, which are really neat. So, what we're going to say is, consider this tree, and consider some branch of this tree. Okay? So every branch you get down, you start at the root with n elements, and then as you go down the tree, you're splitting off, and your subarray is getting smaller, and then when you get down to the leaf, you've got one element, and you say, okay, I'm done, it's sorted. Okay? So you have the root with n elements, and then this splits, and you have like some n, well, this is going to be n2, and then this is going to be, whatever. And so you go down until finally you have 1. Okay? So consider this individual branch. Okay? Now, we're going to consider this as a sequence of, well, sort of coin flips. Okay? So what's going to happen is if I have the array, which is going to be of length ni, ignore the fact that my array here seems to be bigger than my array here. That's like, we don't care. Are people still here? Yes, wow. Dedicated. So we have ni. Now, what I'm going to say is, I don't like it. I consider it a failure if I pick a pivot that's either in the first quarter, so this is also ni over 4, and then if I pick it in the middle, ni over 2, then I'm happy. Okay? So I'm okay, sorry. This is if you consider it sorted. So if I pick, this is not the unsorted array. Sorry. Sorted. Imagine it sorted. So we don't have the sorted array. We have some unsorted array. I'm drawing this picture to say that I want to say, if I pick one of the first, so we're just randomly selecting this start. Oh yes, okay, you already wrote that. Okay. So I should make it Bing when somebody asks a question or something, but I don't know how. So this means if I select as a pivot, pseudo-randomly select a pivot. If it happens to be one of the first ni/4 smallest elements, if it's one of the ni/4 smallest elements, then I'm unhappy, right? Because I'm going to split, and my split is going to be very skewed. If it's one of the biggest ni/4 elements, then I'm also very unhappy because I'm going to split, and it's also going to be skewed. And I'm going to say I'm fairly happy if it's in here. If it's in the middle half, okay? So what is the probability that I'm happy? It's a half. It's like a coin flip. Right? Now, I'm sort of fudging what do you do if there are multiple elements which are the same, but it's actually not bad because when you do the pivot, you can easily identify elements which are the same, and then you actually don't include here, if the pivot is 41, you don't have to include 41 in this subarray because you actually split it into 3. You have like stuff bigger, stuff smaller, and stuff equal. Okay? Because actually, like in the machine implements 3-way comparisons. Okay. So this doesn't look like a quarter, but it is. Okay. So okay, you've got a coin flip. So let's say a failure is when I'm here or here, and a success is here. So how many successes do I need to get from here down to here? Well, notice that even if I get a failure, even if I get all failures, eventually I'm going to get down to here. But I'm going to think, okay, how many successes am I guaranteed to get here? Well, I'm going to need about, notice that every time I get a success, I wipe out at least a quarter, right? So I shrink my array by a factor of 3/4. So that's going to mean I'm going to need log base 4 over 3 n successes. Okay? I look like such a twit doing this. I should erase that in the video. But, okay, so, the thing is, now let's think about this. This is for an individual branch. I'm flipping this coin. And now, if I'm super lucky, I'm going to flip the coin, log base 4 over 3 n times, it's all successes, and I hit the leaf. Okay? So let's think about, but that's if I'm super lucky. That's like if I flip the coin this many times, I got that many heads and no tails. I would have to be really, really lucky. So how many times do I sort of expect to have to flip it? Well, like twice that many-ish. Because if you're flipping a coin, about how much of the time do you expect to get a head and how much of the time do you expect to get a tail? Well, like half the time it's a head and half the time it's a tail. So when I'm doing this, I expect that half the time I'm going to end up, this does not look like half is shaded, but it should be. And then if I get a failure, then I ignore any benefit I get, and if I get a success, then I shrink it by a factor of 3/4. Well, I knock a quarter off. Okay, so that gives you some idea of how this is going to go, right? Because intuitively, suppose we flipped, I had a coin, I'd pull a coin out of my pocket. I actually have, I have coins from other countries. I have like no Canadian coins. When I went to buy the whiteboard, the second whiteboard, isn't this cool? It's huge now. Yesterday, I was asked for